So if you want to join, that's great. As far as popping up on the screen, that's cool. So go ahead, Catherine. You said you had a question.
Yeah, so I'm just looking back over the problem set that we took. So
Which one? The putting it all together one?
yeah, putting it all together. So for oxygen, you have like the sp3 like orbital, I guess, like you have everything filled out.
Yep.
But I was confused because like in 7 with carbon, you have like an extra p, so you have sp2, you have the rest, like you don't have it filled. So do you just not put like the extra electron with the other sp2s, or do you put that into a p? And how do you like, I guess, like figure out?
How do you know? Wait,
yeah.
Where to go? Yeah, that's a really good question. So we're talking about number 7 on the putting it all together problem set. And for those of you that just joined, this is recording, but it's only going to record my face and the screen. It won't record anybody else if you join me. So the question is, with carbon, we have 4 total valence electrons, which is going to put 2 of them in the P and 2 of them in the S. Remember, this is always increasing energy. And in this particular question, it says that we want to make 3 equivalent bonds. So if we want to make 3 equivalent bonds, then we need to have 3 hybridized orbitals. So the number of bonds equals the number of hybridized orbitals, which is going to equal the number of atomic orbitals that we use to make it. So Catherine, I know I'm going kind of around your question, but I'm going to get to it. I just want to kind of put the whole picture together. Atomic orbitals. Okay. So if we want 3 bonds, then we need 3 hybridized orbitals, and we're going to use 3 atomic orbitals. So I'm going to use, and you always have to start with the S because it's the lowest in energy. And I'm going to use the S and 2 of the P's, which create the sp2 hybridized orbitals. And there's 3 of them. So this is an sp2, this is an sp2, and this is an sp2. Okay. So what I didn't mix together was the P. So I'm going to put that down. That's what's left over. And for our purposes here, we can assume that all of these are going to be about equal in energy. Okay. So we have the P's, we have the sp2s, and we are going to half fill them until we run out of electrons. In this case, that means there's going to be 1 in each. Now, if we were to, hold on 1 second. Okay, so if we were to have, let's say oxygen, we were looking at oxygen for this one, oxygen would have 6 valence electrons. So oxygen would give us 1 here and 1 here in the atomic orbitals, and we would have to fit 2 more electrons into this model. So the last 2 would go here and here. So because they're all relatively the same energy, these are exactly the same energy. But I want you to think of them as relatively the same energy for right now, which means we're going to half fill all of them. And then we stop in this case because we don't have any more. If we had more, we would start to double fill them. Does that answer your question, Catherine?
Yeah, kind of. So because it's equivalent, you wouldn't put the extra electron in sp2, you'd put it in the P.
Correct. Yeah, because of it requires less energy to have them separate than it does to put them together, because there's always a little bit of repulsion when you put them together. So it's better to keep them in half-filled orbitals than it will be to pair them. The only time you start to pair them is when you have a big energy jump like we did over here, if that makes sense. So when we filled this one, we filled 1 in the S And then a second one, the S, because we would have to make a big jump up to the P's. So we fully fill this shell before we fill higher energy shell. Since these are all relatively the same energy, we're going to half fill all of them. That's lower in energy than it would be to double fill them. Yeah, Jillian.
I'm just a little confused on why there are 3 sp2 orbitals and then P, because why would you not write like either 4 sp3 orbitals or 1 sp?
That's a good question. So that comes from the question, the paragraph or the sentence, I should say 2 sentences right before number 7 that tell you that we are going to form a molecule that has 3 bonds to it. So an example of this, let me give you an example and that might help. So here is a carbon that has 3 bonds to it and a lone electron. Okay, and it says, what it's asking is, what type of hybridization is this carbon going to have to spread out the electron densities that are in this bond? Okay, so this carbon has 3 things attached to it. We count bonding groups and lone pairs. In this case, we have 3 bonding groups. And remember, we're calling them bonding groups because it doesn't matter if it's a single bond, double bond, or triple bond. This is a lone electron. It is not a lone pair, so we don't count it. We're only counting lone pairs and bonding groups. So there are 3 things attached, 3 things. So we want to spread those out as much as possible. So we want to spread these out so that we get 120 degrees, okay? You don't have to worry about remembering that specific angle. So the way that we know to make sp2 is because we need to make 1 hybridized orbital for every one of these bonds that are attached, okay? So I have a lot of arrows pointing to this, I just realized. Okay, so if we are going to form 3 bonds, we need 3 hybridized orbitals, which means that we need to combine 3 atomic orbitals to make those. So we start with the S, and then we pick 2 P's, okay? So we don't need to mix in that 3rd P because we don't have a lone pair or a bonded group that we would need a hybridized orbital to hold those or to make a bond with. Does that kind of answer your question?
Yes, it did. Thank you.
Perfect. You're welcome. Awesome. All right. Any other questions on, so once again, we're just looking at the putting it all together. There was an error in the key that I originally put up. So if you're looking at number 15, sorry, let me see if I can stop. I know if I change what I'm sharing, it'll never come back up again. Hold on, let me go this way. Putting it all together key, here we go. If you downloaded it early, please go back and look. The numbers here were not correct. I think there was like a 4, 3, and a 2. Okay. So you want to look at those numbers right there. There's also like an extra structure here. I'm not sure why. And it said old lone pairs in the key, and I don't know where the word old came from. So I just took that out too. All right. So anything else you guys want to talk about on the key, on the putting it all together?
Dr. Nolan.
Yeah.
Oh, there's a lot of echo. Sorry.
No worries.
Sorry, we have 2 computers out. For 15, the chart, I was just noticing one thing. So you had 1 bonding domain and 1 lone pair. Oh wait, never mind. I had a different hybridization. I did that incorrectly. That was my fault. Okay.
You're okay though? You're good?
Yes.
Okay, great. All right.
I have a question.
Yeah, Boomer, go ahead.
In like the 16 and 17 questions,
Mhm.
there's like so in the 16th one and the 17th one, like the orbitals are like drawn differently. Like in 16, it is first like phi and then sigma.
Right.
And, like, how are we supposed to know that, or like how do we decide that?
Yeah. So first, you're not expected to know that yet. That's something that if you take Chem 317, which is inorganic, you'll learn a little bit more about why that is. It has to do with the orbital size and the relative energies. But you would be given this whole, well, I should say this whole energy diagram you'll be given. So you don't have to worry about where that switch takes place. It only happens in the first row, and it happens between nitrogen and oxygen. That's where that switch takes place. But I don't expect you to be able to predict when and why that would happen. Good.
Yes, thank you. And also like in the 15th one for
15.
H2S,
Yes.
like how do you decide the bond angle?
The bond angle, great question. So it really has to do with what the hybridization is. So the hybridization, if you have sp3, that hybridization, oh, it's written right here. sp3, it's 109. sp2, it's 120, and sp, it's 180. And that all comes from how we're spreading out the groups. So sp means that everything is in a linear fashion, which means that just turned into an arrow. So that means that everything is 180 degrees. When we're sp2, that means that we have 3 things attached to the central atom. And the best way to spread those out is if you have bond angles of 120 degrees. And then with sp3, we're talking about a tetrahedron shape. Oops, sorry, that should be a little bit nicer here. So the wedge means it's coming out at you, and dashes mean it's going away from you. Okay. And the bond angles here are 109.
So it's directly about like hybridization.
Yeah, exactly. Yeah.
Thank you.
You're welcome. Good.
Will you please go over 4 and 5?
4 and 5? Absolutely.
Yes.
Okay. So 4 is asking you to draw a similar diagram to the one that was given above for an sp3 hybridized oxygen. Okay, so what I'm going to do, because I want to stop writing on the answer key, is jump here. So we want to draw the energy diagram just for an sp3 hybridized oxygen. So we start off by thinking about the atomic orbitals. So everything in that row, we're just going to be considering the 2s and the 3 2p orbitals. Okay. So the first part of the question is determining how many valence electrons oxygen has. Okay, so we go to the group number, it's in group 6. So oxygen has 6 valence electrons. Okay, we're going to fill that up starting at the bottom, 1, 2. Then we fill the p's, and we're going to half fill them first, then add the next one. So how many do we have? 1, 2, 3, 4, 5, 6. Okay. So the key to this is the description that says draw the energy diagrams for sp3 hybridized oxygen. So that means that I'm mixing together the S and the 2 P's. Okay. So let me say that a different way. I'm mixing together the 1, 2s orbital and all 3 of the 2p orbitals. And out of that, I make 4 sp3 hybridized orbitals. So this is sp3, this is sp3, this is sp3, and this is sp3. Okay, so it's going to keep the same number of electrons. It's just changing the shape of the orbitals. So we still have 6, so we're going to fill this in 1, 2, 3, 4, 5, 6. Okay. So 5 is asking how many sigma bonds are formed. And then number 6 is saying, what are the other sp3 hybridized orbitals used for? Well, let's think about what this is telling us as far as these little lines we've drawn in. So when we have 2 lines in the orbital, that tells us that the orbital is full. So this one is full and this one is full. So these 2 are full. Okay, which means they won't form any bonds. The next 2 are half full. So we can add another one here and another one here. And what that does is it fills the valence shell of our oxygen if we bring 2 more electrons in, which means that these 2 are going to participate in bonding. Okay, they participate in bonding so that they can each get 1 more electron to fill the valence shell. So we are going to look for these half-filled orbitals to determine how many bonds can be made. So if we have 2 half-filled, this is going to tell us that we can make 2 bonds. Okay. The hybridized orbitals are used to make sigma bonds. The unhybridized p orbitals are used to make pi bonds. So you can assume now, since we're talking strictly about the hybridized orbitals, that these will all be sigma bonds. Okay. So then what is happening with these 2 full ones? Well, these are pairs of electrons on the oxygen that are not being used for bonding. That, another way of saying that is they are lone pairs. So what we're looking at here is an oxygen with 2 lone pairs and 2 lone electrons that are waiting for another atom to come and make 2 bonds. So we can imagine hydrogen could come and bring 1 electron with it. Another hydrogen can come and bring 1 electron with it. Those electrons would join with the half-filled valence shell electrons to make new sigma bonds. Okay, so these are the lone pairs. And that's what those last few sp3 hybridized orbitals are used for. Good? Okay, great. Beautiful. Anybody else have a question on that?
So if unhybridized shows pi bonds, can you give an example of that? Just
Yeah,
because I feel it
absolutely.
lost.
Let's take a look at so let's take a look at trying to think of a diatomic molecule that has a double bond but not a triple bond. I'll just draw one. So here's a carbon. Oh, no, that is a highlighted mark. So here's a carbon. And let's pretend this carbon is sp2 hybridized, which means that it has 3 different things attached to it. Okay. And it's going to join with an oxygen that is also sp2 hybridized. So it's going to have 3 things attached to it. 1 is a sigma bond, and 2 are lone pairs. So that means for each molecule, we took the S and 2 of the P's to make the 3 sp2 hybridized orbitals, sp2, sp2, and sp2. So what was not hybridized is the p orbital. And that p orbital is going to be perpendicular to where all these other orbitals are, which I'm not drawing in right now. And it will overlap with the p orbital that's unhybridized on oxygen. And these 2 will form a bond above and below the plane. Okay. So the sp2s all make the sigma bonds, and the p orbital that's left over makes the pi bond. Does that kind of answer your question? Or do you want me to go into more detail?
Can you go into more detail, please? I'm a little bit confused.
Sure. No. It's all brand new stuff, I'm assuming. Is it the idea of the pi bond or the way that the p orbital overlaps, or all of it?
All of it.
All of it, no worries. Okay, so let's kind of take a step back for a second and talk about the fact that we have two different types of bonds. I don't want to say types. Let's say two different shapes of bonds. We have one shape of bond that we call a head-on bond, which happens when two orbitals overlap like this. And there's this area where they overlap, which is kind of where they're sharing the electrons and that bond is formed. And this is a sigma bond. And we make these according to our VSEPR theory using hybridized orbitals. So these are why can I not spell and talk at the same time? So these are hybridized. Okay, so in the molecule that I drew over here, this carbon has 3 different sigma bonds. So that carbon has 1 sp2 hybridized orbital, 2 sp2 hybridized orbitals, and 3 sp2 hybridized orbitals. And I'm going to color those yellow here. Okay. It uses those hybridized orbitals to make sigma bonds. So the oxygen that it's attached to, oxygen, also is sp2 hybridized. So it's going to make a sigma bond using one of its sp2 hybridized orbitals. And the other 2 have lone pairs in them. Okay. So those are all the way that the hybridized orbitals are being used. So we're not showing any specific type of group attached here, but let's pretend, let's just make life easy and make them hydrogens. Hydrogens only have an s orbital, so we'll just stick them down here. Once again, this overlap right here is where the bond is happening. Is that much pretty good for everybody?
Yeah.
Okay, good. So when these molecules are forming, we are having these head-on overlaps, but we do have these leftover p orbitals that have not been hybridized, which have a lobe above and a lobe below the plane. Okay, don't worry about above and below the plane. Let's just worry about the fact that we have these p orbitals that are not being used in hybridization. They also have 1 electron in them each. So we're bringing next to each other these 2 p orbitals that have 1 electron in them each. And what's going to happen is that they start to attract each other because they want to both share that 1 electron and fill their valence shell. So what ends up happening is that we get this attractive force that happens between both lobes of these p orbitals. Okay, and within that lobe are 2 electrons that make up the pi bond, which is the second bond of a double bond. Roz, how's that? Do we need a little bit more?
Are the 2 electrons inside, do they come from, are they just are each of them just the electrons from the individual pi,
That's a really good question. So before these come together, we can think of the carbon being like this. The carbon has its p orbital with 1 electron, and I'm going to make that right here. Okay. And it has its sp2 hybridized lobes, each with 1 electron. I'm going to color code these. Here's 1, here's 2, and here's 3. Okay, so carbon has 4 valence electrons. It takes those 4 valence electrons and it puts 3 of them in hybridized orbitals when it's going to make 3 bonds. Sorry, it takes 3 of them, puts them in 3 hybridized orbitals when it's going to make 3 bonds. The last one here that we left in black is going to be the one that's left over in the p orbital. Okay, so this one right here, the pink one, is the one that's going to be used to make the sigma bond to oxygen. So I'm going to bring oxygen over with its funky orbital, and it brings, and I'm going to use X's for the oxygen. So those 2 electrons are being used, one coming from carbon, one from oxygen, to share and make a sigma bond. Does that part make sense?
Yeah.
Okay, good. So imagine oxygen's the same way. So oxygen has a lone pair in one orbital, a lone pair in the other orbital. Let me draw out those orbitals. So it is sp2, 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 and the leftover p. So oxygen has 6 valence electrons. So there, oh, I shouldn't have done that color first. We have 1, 2, I'm not doing, you don't fill them in this order, but I'm doing it this way because of colors, just to make it easier. All right, so if we were to fill this, we would do 1, 2, 3, 4, 5, 6. Okay, 1 pair of electrons is this blue lone pair. 1 pair of electrons is this green lone pair. The pink one right here is being used to make this sigma bond, which leaves this black one left over in a p orbital. So here's that giant p orbital. Oh, looking funky. P orbital that has the 1 black electron in it. So as these two atoms are getting closer together, the 2 black electrons are going to get attracted to each other so that they can make a pair. And that is going to be what causes the sharing between these 2 p orbitals. So these 2 lone black electrons now become a bonded pair in a type of a bond that's shaped differently than a sigma bond, and we call it a pi bond. Yeah, no?
Yeah, that makes more sense. Thank you.
Good. Yeah. Keep asking until, it feels a little bit more comfortable.
I'm sorry for staying on this, but if only 1 electron is coming from each, then how does it make a pi bond? I thought you needed more electrons than that.
Okay, so I want to make sure we're talking about a pi bond and not a double bond, because this molecule, and I'm going to draw it like this. Okay, which has 2 other bonds to it. So in between the carbon and the oxygen, there's a double bond, which is a sigma bond plus a pi bond. The sigma bond is coming from these 2 pink electrons that are being shared. That's the sigma bond. The pi bond is coming from the 2 black electrons that are being shared. Okay, so those 2 are making the pi bond, a total of 4 together in the double bond. Good, okay, good, beautiful. Okay.
So it's only 1 pi bond for that in total?
Correct, exactly. 1 sigma bond, 1 pi bond. An example of 2 pi bonds would be something like carbon monoxide, which looks like this. Okay, carbon monoxide has a triple bond, which means it has 1 sigma bond, which has 2 electrons, and it has 2 pi bonds, each with 2 electrons in them, to give us the grand total of 6 electrons. Good?
I have a question.
Sure.
Are we supposed to be like drawing these like orbitals, like to symbolize like hybridization. So
So are you going to be asked to draw something like this?
mhm.
Not yet. No, that's organic. The first part of organic is when you're going to be drawing these. I think it kind of helps to be able to visualize it, at least for me, because I'm a visual person, to understand how the bonding works. But for right now, excuse me, what I would expect you to do is this. I would expect you to approach a molecule, this one's called formaldehyde, and be able to say, okay, this carbon has 3 things attached to it. It has 3 bonding domains. So that means it is sp2 hybridized. And that it has a geometry of trigonal planar. Does that make sense? That's what I would expect you to be able to do right now.
Yes, thank you. And like and I have a question about the orbital's energy, like so like SPs are lower than a p orbital, right?
SPs are lower than p orbitals, yes.
So
A
like,
little bit, yeah.
for example, in sevens, like
Yeah.
for example, why are we like going up to the p orbital rather than like filling the SPs first?
You're on number 7? Yeah, okay. So for our purposes here, the best way for me to explain it is that they're relatively close in energy. There is definitely a stabilization for going down and bringing in some s orbital. So in reality, I would say that these are probably more like this, where you have a little bit of a difference between the two. Okay. But it's not enough to promote them to a higher energy orbital. I'm sorry. It's not enough to, let me say it this way. If the jump was this big, I would say, okay, if we're talking about carbon, we would do 1, 2, 3, 4, but it's not as big of a difference. So we're going to keep them half filled and save that energy that it would cost to pair them up. Good.
Yes, thank you.
You're welcome. All right, how are you guys feeling on your geometries and such? Should we do an example?
Yeah.
Thumbs up. Okay. Beautiful. All right. So let's start with this one. So this is silicon tetrafluoride. All right. So we want to figure out, let's see, we want to do the Lewis structure. And then we're going to do the electron domains, the electron geometry, the molecular geometry, and the hybridization. Okay. So we'll do this for like a couple of them. All right. So we start with silicon tetrafluoride. So silicon is right below carbon. So that's in group 4. So that's going to bring 4 valence electrons. Fluorine is in group 7. So it is going to bring 7 electrons, and there's 4 of them. So it brings a total of 28, which gives us 32. Right? I think that's correct. Okay. So we need to know which atom's going to go in the middle. You may be able to guess, but remember, it's going to be the least electronegative. Another way of saying that is the one closest to the center of the periodic table. So that's silicon. So we would draw silicon with 4 fluorines attached. All right, so that's how many lone pairs we have, or how many electrons? 2, 4, 6, 8. So we need to fill in some lone pairs here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay. So now we want electron domains. Remember that this means how many lone pairs plus bonding groups. So we don't have any lone pairs on silicon, but we have 4 bonding domains. So our electron domain is 4. Okay. So 4 is going to give us the electron geometry, which is tetrahedral, tetrahedron, tetrahedral. Now, going to the molecular geometry, the only time it's different is if there's a lone pair on that center atom. This case, silicon doesn't have a lone pair, so these are going to be the same. So this is also a tetrahedron. Tetrahedral. Okay. We have 4 things attached, 4 electron domains. So that means that we need 4 hybridized orbitals in order to make those bonds. So that means I need SP what? 3. Okay, this is where my little trick with the I keep wanting to say exponents. The superscripts come in, because if you remember that there's an understood 1 here, if you add together these 2 numbers, that's going to be your number of your electron domain. Okay, so if your electron domain is 3, it's going to be sp2, because 1 plus 2 is 3. Okay, that's where my little trick comes in. All right, any questions on that one? Not so bad? Okay, how about, all right, let's do one where it's a little bit, where it's different. Let's do a funky one. So here's a funky one. We are going to do selenium tetrachloride. Okay. All right, so selenium is underneath sulfur, which is underneath oxygen, so it's in group 6. So it's going to bring 6 electrons. Chlorine's in group 7, so it brings 7 times 4 is 28. So this is going to be 34 electrons. Right? Please stop me if you need me to talk about Lewis structures at all. So closest to the center of periodic table is selenium, and we're going to put the 4 chlorines around it. So you may jump at this point and say, oh, okay, we got 4 bonding domains, we're going to be tetrahedral, and if you do that, you're going to be wrong. So make sure you go through and completely do your Lewis structure, and I'll show you why here. So we have, so far we're showing 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We still have 2 electrons to go. They get placed on the central atom. Okay. So if you have extra electrons, they go on the central atom. Usually that central atom is a bigger atom and is able to expand out its shells a little bit. So that's why it goes on the central. So electron domains now is going to be the fact that we have 4 bonded groups plus a lone pair. So now we're at a bonding domain of 5. So what is the geometry? Let's do the electron geometry first. 5 groups give us trigonal bi, I always spell this wrong, bipyramidal. I always want to switch the I and the Y. I don't know why. Okay. So what is this going to look like? Well, we kind of try to visualize this. We have chlorines that are going to be opposite each other. And then near the middle here, we're going to have, oh, sorry, I put a hydrogen. We're going to have a triangle around the middle. So we're going to have Cl, Cl. And sometimes I'll draw it like this, so it almost looks like a bonded pair like this. Okay. So when we go from electron domain to molecular domain, I'm sorry, geometry, we need to account for the fact that now we have a lone pair, okay? Which means that basically becomes invisible in the molecular geometry. So the molecular geometry for this one is going to be seesaw. Okay. And that's because if we kind of turn this sideways, let's see if I can do this. If I turn this sideways, can you kind of see where like these are the sides of the seesaw and this is the stand that it's in, and it would go like back and forth like this? If not, it's okay. I don't necessarily expect that you'll be able to say, okay, it's seesaw, or it's going to be, I guess for this one, seesaw would be, oh, it could have been here. So what I don't expect you to be able to do just yet is be able to know that this lone pair would be in the what we call the equatorial position. You could have opted to put it on an axial position, okay? And if you did, and this part became invisible, you would end up with a trigonal pyramidal type of a shape, okay? For me, that's fine right now. It's most important that you realize that these two would be different because there's a lone pair there. Seesaw and the trigonal pyramidal are both subsets of this molecular geometry group. Okay, does that make sense? For both, yeah.
The electron geometry and molecular geometry are always different if there are lone pairs present.
Exactly. Yep, you got it.
Okay, thank you.
Perfect. All right, so now the question is, what's the hybridization? Well, how many things do we have? We have 5 things, right? 5 electron domains. So that means I need 5 molecular orbitals. So, I'm sorry, hybridized orbitals. So I'm going to start with my S. I only have 1 of those. P, the most I can have are 3 because there's only 3 p orbitals. That gets me up to a total of 4. So now I'm going to have to bring in a d orbital in order to have enough atomic orbitals to mix to give 5 hybridized orbitals. Because remember that the number of atomic orbitals has to equal the number of the hybridized orbitals. Okay, we only have 3 P's, we only have 1 S. We have 5 D's that we can work with. So that's why we bring a D in here. Good?
Dr. Nolan,
Yeah.
can we do an example that we can write out the hybridization electron diagrams? Yeah, this is Jackie's question. She's sitting behind me. I'm asking for her.
No worries. Where you're asking if we can draw the MO diagrams, is that what you're asking?
Not that like the valence electron, like the arrows just on the little spaces.
Oh, like the levels with the lines.
Yeah. So in this case, I mean, we could do it with this one. This is fine. So our central atom is selenium, which we said has 6 valence electrons. Okay, so its hybridization is sp3d. So that means it's going to have 5, 1, 2, 3, 4, 5 sp3d orbitals, sp3d, sp3d, and these are all the same. So I'm just going to say ditto. Everybody knows that those 2 lines just mean like repeat, means the same all the way across. Okay, so 6 valence electrons, 1, 2, 3, 4, 5. Now we're gonna have to double up 6. These 4 half-filled orbitals are the ones that are used to make the sigma bonds. It wants one more electron. It wants to share with another atom to make a sigma bond. This filled orbital, this lone pair right here. We could do the same thing for silicon up above. Silicon has 4 things attached to it, which made it sp3 hybridized. So we have 4 sp3 hybridized lobes, sp3, 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 sp3. It has 4 valence electrons. So I'm going to fill those up. 1, 2, 3, 4. They are all half filled, which means that silicon is going to want to make 4 bonds so we can fill all those orbitals and have a full octet. And that's exactly what we see here. Jackie, is this kind of answering your question?
Yes, it is. Thank you.
You're welcome.
One other thing, say, do you think we could maybe do an example like this where there would be a pi bond?
Where we have a pi bond for, for the bonding geometry, you mean, for that part?
Yes, I think just all over how it would affect the, like, all these different like categories as well.
Yeah, absolutely. Let's do, have a bunch of friends. Give me 1 sec. Ooh, that one would be tough. All right, let's do CO2. Let's do CO2. So we have CO2. Okay. So carbon brings 4 electrons. Oxygen is going to bring a total of 12. So that means we have 16 electrons. So we have carbon bound to the 2 oxygen. Carbon's in the middle of the periodic table, so that's why it gets the central. So it's 2, 4, 6, 8, 6, 8, 10, 12, 14, 16. All right, I have a problem. I don't have full octet on my carbon. So I'm going to use 1 lone pair from this oxygen to the left and make a double bond. I'm going to do the same thing with the oxygen on the right. I'm going to use one of its lone pairs. And we end up with a Lewis structure like this. Okay. All right. So the electron domain, this carbon has 1 bonding group to the right, 1 bonding group to the left. So this would be 2. Its electron geometry only has 1 option, and that's linear. No lone pairs on the central carbon or the central atom. So the molecular geometry is the exact same. Okay.
Really quickly,
Yeah,
is there anything besides lone pairs that can change whether or not electron geometry and molecular geometry are the same, or is it only the lone pairs that would change that?
That's the only thing that changes it.
Okay, thank you.
Yep, you're welcome. So I think hybridization was at the next thing. Yeah. So hybridization, we have two two electron domains. So we're going to need two hybridized orbitals to fulfill those. So I need S and only one P, because that would give me two sp hybridized orbitals. So if I were to think about this carbon atom, I'll do the whole thing. We start off with 1 2s orbital and 3 2p orbitals. We combine two of those to make two sp hybridized orbitals. Oop, that got gigantic there. And we have two p orbitals left over, p and p. We have 4 valence electrons, so we fill those in. And then we fill in the hybridized orbitals and the unhybridized orbitals. Now, you'll notice I drew them at different energy levels. I tried to show these as pretty close. There is a slight difference between them, but I think I can say never, being careful here. But for all the examples I can think of where you're always going to half fill all of these, both the hybridized and unhybridized, before we ever double up anything, okay? So these two orbitals are used to make the two sigma bonds. The two p orbitals make the two pi bonds, Okay, let me show you where those are. In between the oxygen and the oxygen to the left in that carbon is a sigma bond plus a pi bond. To the right is a sigma bond plus a pi bond. Okay, so that's where those come from. I think we covered everything with that one.
So did you only combine the S and then the P's because the electron was 2?
I'm sorry, I couldn't make out what you were saying.
Did you only combine the S and then the P orbitals because the electron domain is 2?
Yes, I only combined the S and a P orbital because that electron domain was 2. So I only needed 2 hybridized orbitals to do that. And that means I needed 2 orbitals that we call sp. Exactly. Okay. I can't remember who asked for the multiple bond one, but does that help?
I think it was me. Thank you. But one more question. So why not just why create the extra 2p orbitals instead of just putting those electrons with the sp and filling both of those orbitals?
Ah, that's an interesting question. So if I took these 2 electrons and put them in here, I would get something that looks like this. 1, 2, 3, 4. What do you think about these? They're both full, which means that they wouldn't bond at all. So what this would become is a carbon that has 2 lone pairs on it at 180 degrees from each other. That's what that would look like. And that's all its electrons, meaning it would only be able to have 4 electrons, okay? It would have to have them as lone pairs, and they would be at 180 degrees. Let me say that slightly different way. Carbon only has 4 valence electrons, so it wants to make 4 bonds. By leaving all of these half filled, it allows itself to accept 4 electrons to fill those orbitals and fill the shell and get to a full octet. So it is beneficial for its bonding, which means it'll be lower in energy, having them half filled so that they can accept electrons and make a full octet for a carbon.
Okay, that makes sense.
Oh,
So
pretty good.
you have say you have 2 electrons in a place, that means you have a lone pair. if you know that you have sigma bonds, you have all the electrons spaced out over four of the same orbitals. And if you have a pi bond, you know that you have to have a separate orbit, 2 different orbitals going on there.
At least 2, right? So if you have a double bond, you're going to have hybridized orbital. Ooh, didn't mean to do that. You're going to have hybridized orbitals and 1 p orbital to make that pi bond. This is not an example of that. Let me, you'd be like this if you had 1 double bond. If you have a triple bond, you would now be sp, because you need 2 different p orbitals to make the 2 different pi bonds.
Okay.
But I think how you're thinking about this is 100% correct.
Okay. Thank you.
You're
That's a
welcome.
very long question.
Did you say you had one more, or that was a long one?
No, I just said that was a very long question on my part.
Oh, I'm sure everybody else listening learned something from that. Okay, so we talked about electron domains, electron geometry, molecular geometry, hybridization. We talked a little bit about MO diagrams. Let's do one. Oh, we did CO. That was the one I wanted to do. Oh, let's do the bond order. So let's determine, excuse me, the bond order for carbon monoxide. Okay, so let's pretend you don't know what it looks like. So I'm going to erase it. No, it's not letting me erase it. There we go. Okay. No, we didn't do that one. Never mind. That was earlier today. Earlier today, it's all starting to flow together. All right, we're going to do carbon monoxide. So this is CO. Okay. We did carbon dioxide. That's why I was getting confused just a second ago. So what would you be given? So this might be a question where it says, fill in the valence electrons and the molecular electrons for CO in the given molecular orbital diagram. Okay, so you would have to be given the following. So we have 2s and 3 2p's. And let's say this is carbon. And then we would have oxygen 2s and oxygen's 2p's. Okay. So are there 1s orbitals? Yes, but they're buried deep inside and they're not going to be involved with bonding, so we're not going to worry about them. Okay, so these areas are just for the atoms. We have not talked about the molecules yet. These are just the atomic orbitals. So the part in the middle, which shows the molecule, will be given to you. And that's going to look like this, where we have a sigma and a sigma star. And then we'll have a sigma, 2 pi's, 2 pi stars, and a sigma star. Okay, and it probably has some dashed lines attaching like this. I'm gonna move some things down just a little bit, just so it's a little clearer for us as we're looking at this. Just scooted it down. Connecting the lines, connecting the lines, connecting the lines. I think it just makes them more complicated, but hey, this is how they do them. Okay, so once again, outside are the atoms, just like we've been doing for things like up here, okay? In the middle is where the atoms come together and form the new molecular orbitals. So carbon has 4 valence electrons. So we're going to fill up its atomic orbitals just like we have been doing. 1, 2, that's full, so we need to jump to the next energy level. 1, 2. So that's a total of 4. We're done. Oxygen has, oh my goodness. Do you guys see I said 2 valence electrons for carbon? That is 4 valence electrons right here. Okay, just want to make sure you see that. All right, oxygen, 6 valence electrons. So we're going to fill up its atomic orbital, starting at the bottom, 1, 2, and then we're going to keep going. We have to jump up to the next energy level, which is the 2p. So here's 3, 4, 5. We're not done, so now we need to start pairing. Here's 6. Now we're done. Okay, so we have the 2 atoms. Now let's bring them together and fill up the molecular orbital. So now we need to look at total electrons. We have a total of 10 electrons in the molecule. So we're going to fill those in from the bottom up. I can even ignore everything that's going on this side now and this side now. I don't care about those. I just need to worry about the middle. So we'll start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I'm going to pause for a second. Give me a thumbs up if you're okay. Okay, beautiful. Thank you. Okay, so now that's all you need to do to fill in your molecular orbital. That's it. Okay, we add together the valence electrons and we fill in the middle from the bottom up, just like we would for atomic orbitals. So now we want to determine what the bond order is. That tells you how many bonds are between the 2 atoms. So to determine your bond order, you're going to add together or sum up the number of bonding electrons. You're going to subtract from that the number of electrons that are in the anti-bonding orbitals. And you're going to divide that by 2 because every bond has 2 electrons in it. Okay, so how do you know whether or not you have a bonding or an anti-bonding orbital? You're looking for these little stars. So these little stars are what are going to tell you they're anti-bonding orbitals. They're the ones that are higher in energy than the atomic orbitals are. Okay, if it doesn't have a star, it's not an anti-bonding orbital. Okay. So let's count up bonding. We have, let me change colors here. We have 2 here. Those are, okay, so we have 2 bonding. The next orbital is anti-bonding, so we're going to skip that. We're going to the next one. Yep, that's bonding. So now we're up to 4. Go up to the next one. These 2 are pi, but they're not anti-bonding, so we're going to count those. So we're at 2, 4, 6, 8. So we have a total of 8 electrons that are bonding. I'll just write bonding on top. We're going to do the bond order. Let's count anti-bonding. So now we're going to look for those stars. So we go from the bottom. Here's, ooh, here are 2 right here. And I'm going to keep looking. All the other ones are all empty. So I only have 2. So we have 2 minus 2 electrons that are anti-bonding. We're going to divide that by 2. So 8 minus 2 is 6. Divided by 2 gives us 3. That tells me I have a triple bond. The order of bonds is 3. That means triple bond. And the structure of CO2 or CO looks like this. I'm going to draw it off to the left-hand side here. There's my carbon, triply bound to an oxygen. And both the carbon and the oxygen have a lone pair on them. Okay. So once again, we know there's a triple bond because of the bond order. They're sharing a total of 6 electrons. This is where they are right here. And it even tells you one of them is a sigma bond. 2 of them are pi bonds. Okay, that's your triple bond. The ones down here cancel each other out as far as bonding. So I have 2 that are bonding and I have 2 that are anti-bonding. So they're just not really adding to any bonding at all. Those 2 sets of electrons are the 2 lone pairs. I think that's kind of cool.
If the bonding order was 2, would that be a double bond?
It would be. Bond order of 2 is a double bond. Exactly. Yep. And you can have bond orders that are not whole numbers either. And that just means that there's some type of attraction between them, that maybe 2 atoms are sharing 1 electron. It's a very odd type of bonding, but it can happen. Go ahead. I think Catherine, you were saying something.
I was gonna
Oh, awesome.
ask, like if you had like a molecule, do you have to, so if you have a molecule with more than just 2 atoms in it, do you have to do this for each separate bond in the molecule?
Oh, that's a really good question. It's a little bit different. You have to look at how the individual atomic orbitals combine in groups. And it's pretty advanced, but you start to do that in inorganic chemistry. But it's a lot further than we are right now.
So do we only have to do like molecules like this that only have 2 atoms in it?
Exactly. Yep. We're going to stay with diatomics.
And then like, so, okay, so we wouldn't have to do like CO2?
Correct. Yep. Exactly.
Okay, thank you.
Yeah. You're welcome. All right. Any other burning questions that you may have? Except for what are the answers? We're good?